Good evening, everyone. Wonderful Wednesday, and welcome to RASC Toronto Centre. We are online tonight again, and I am Dr. Elena Hyde, the second Vice President of RASC Toronto Centre. This is April, whether or not we believe it, it's April 2022 already, and this is our Speakers Night presentation. This is one of two types of gatherings that we have online these days, not at the Ontario Science Centre due to the pandemic, but here on YouTube. Later on tonight, our president, Tom Luton, will be talking about our various programs. But first, we have a very special event to kick off, per usual. So, to get us started, I'll go ahead and begin with our acknowledgement that the Royal Astronomical Society of Canada Toronto Centre meets on the traditional territories of many Indigenous nations, including the Haudenosaunee Confederacy, the Huron-Wendat, the Mississaugas of Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Islands. As we engage in astronomy here, together we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, and the earth. Now, to get us started for our speakers night tonight, I am really delighted to welcome Dr. Carl E. Fields, a Feynman Distinguished Postdoctoral Fellow at Los Alamos National Laboratory. Now, that sounds like a lot. Just wait until I actually get to his introduction here. Dr. Carl E. Fields, or Carl, as he'll go by in this particular show, he got his PhD at Michigan State University and now specializes in some really extreme simulations of massive stars. That's right, those really, really big ones, and they're energetic stellar explosions. So, obviously, I'll let our speaker talk all about that. And this is some very, very dynamic topics. And I'll just point out that he not only researches massive stars, but also looks at really large scale tools for these big questions: computational physics, exascale machines, astroparticle physics, and even more. So before I get too distracted by the awesomeness of this sort of startling talk, I'm really interested to get into and hear more. Now, of course, because we're looking at some beautiful simulations, I hear that there are some amazing videos. So go ahead and without any further ado, Carl, please take it away and show us what you got.
I want to start off by thanking the organizers for inviting me to talk today and share some of my research, as well as some of the research by some of my colleagues, as they walk us through this journey discussing the remarkable death of a massive star. I hope by the end of this talk that we'll have a deeper understanding of the role that stars play in our own galaxy, but galaxies throughout the universe. Um, and so the way I want to start off with this is maybe with an image that might be more familiar to us, something that we might have experienced here on Earth, something that might be we might remember a part of. And so there's this image here that I'm sharing. It's a composite image, means a collection of multiple images placed together, titled "Planets Rising Beyond Alien Throne Rock," which is a monument in New Mexico, actually, which is where I'm giving this talk from right now. And so shown here in this image, we have Saturn, a planet in our solar system. We also have Jupiter being shown. We have something that I imagine a lot of folks might be familiar with, the Milky Way arm that's shown as this across the sky here is this beautiful part of this image. But within this Milky Way arm, there are a lot of different components that make up what go into our universe and our galaxies and other such galaxies. Part of that is gas. So that gas helps evolve these galaxies. It also contains dust, which has a different definition depending on who you ask within the community. And also it contains stars. And that's what I'll be focusing and talking about tonight. But when you look up into the sky and you might see the arm of the Milky Way, or whatever part of the world you're in, hopefully we can gain a deeper understanding of the role that stars play in our own galaxy and throughout the universe. So observations of stars have done really great things. And so I'm really excited to share some of these images, which will be the first of many, where here we have a composite image from Hubble Space Telescope of what's been known as the hourglass planetary nebula. And so this image is remarkable in that it shows something very um, asymmetrical, something very unique and complex that is the end result of a star. And so for this particular star, this was the end fate of a low mass star, so a star with a mass that's similar to that of our sun, if you will. And it's been dubbed a planetary nebula, which is actually a misnomer because this image that we're seeing is the outer envelope being shed of a sun-like star, and actually doesn't contain any planets. And so in the center there, we actually have the remainder of that star, that core that's left behind. But these are some of the things that we've been able to observe that have been able to advance our understanding through observations of stars like our sun in later phases of their life, but also at massive stars. And so here we're showing a composite image again of a supernova remnant, where if we define this, is actually the aftermath of a stellar explosion of a massive star. And so these big plumes of gas that are being pushed out and mixed into their surroundings are the end result of a massive star exploding. And I'll talk into more detail of some of the steps that it takes to get to that process. Within that observation, you can actually see what's called the neutron star, which is the remnant of this collapsed core of a massive star. So in a similar way to a solar-like star, massive stars can often leave behind that collapsed core that caused and drove the explosion. And understanding each sort of phase of a star's life through these observations has really catapulted us forward in advancing our understanding of the role that they play throughout galaxies and throughout our universe. And so you might ask, what exactly have we learned from observations of stars? And some of the things that I like to point out um, are that we know that stars produce elements. And so stars produce elements needed for life. This is something that's been said often by Carl Sagan, we are star stuff. And they also produce the elements necessary or that help feed into the future generation of stars. And so stars will explode, their material will mix into the surrounding environment and then reprocess to form a future generation. This is a very important way that stars can help move forward and evolve different galaxies like our own, the Milky Way. And in that same sort of note, they evolve galaxies, right? And so some of the specific ways they do that is providing energy. So when they explode, that moving energy of that shock or that envelope being pushed out over time actually helps to drive the evolving of the galaxy. And so that's one way that they do it. They also provide that mass. And so material that's needed to go into these future generations help drive the evolution of galaxies. And something I sort of alluded to a little bit earlier is that they produce remnants. And so what's often done is a massive star will explode and then they'll produce this collapsed core that's in the center, whether it be a protoneutron star or a black hole. I'll talk in more detail about what those are. But the point that we've been able to observe is that they leave behind something, and that something can help also fuel the next generation of new transients that can further produce different elements, unique elements that can further help evolve these different environments that stars live in. One of the challenges, though, is that observations alone has not allowed us to come to a complete understanding of stars, and there are many reasons for this, and I'll hopefully highlight a few here that really motivates some of the reason for a lot of my work and a lot of the work that folks do in different subfields relevant to stars. And so you might ask the question, when are stars not enough, or when observation's not enough? That is, and one of the things I like to think about is in our model of the sun. And so here I have a diagram on the right, artist representation of what the sun might look like when you look into the interior. And so at the very center, we see that there's a core. This is where the sun is undergoing hydrogen fusion, where it's fusing hydrogen to heavier elements into helium specifically. Above that is what's called the radiative zone. And so this is a region where heat is being transferred via conduction, which is contrary to the region above that, which is called the convection zone. And the convection zone is very important in many stars, but specifically in our sun, because this zone, how we characterize it, is very important for trying to probe the interior of the sun, a region that's inaccessible by direct observation, So we have to actually couple our models and our understanding of how convection works through direct observation and through theoretical models. And so when I talk about convection, I talk about water boiling in a pot, where energy is transferred via mass motions. This takes place on the surface of the sun, and how we understand that shapes our understanding of our own sun. So what you can actually do is you can observe small changes in brightness over time in the sun using different techniques. And then what that allows you to do is probe something called sound waves within the sun. So sound waves are unique because they can actually travel through the entire sun. And so if you're able to get an accurate description of these sound waves and how they travel through the sun, you can get a deep understanding of what the stellar interior looks like, something that is otherwise inaccessible and is a challenge to model. And so this begs the question, observations eventually become not enough when you have to couple them to complex computational models, in this particular case of convection, because you need to understand how these waves transport energy and material through the sun. Um, and so there's been a lot of work in building computational models, and that's what I'll focus on for the rest of this talk, is how we can couple observation to computational models of stars. And so there's a lot of ways that folks have been doing this in the past, where they've been coupling modern observations to computational models of the star. One example is in constraining surface convection. So convection in our sun, just like I talked about previously, um, folks have been able to run simulations, very large scale simulations on supercomputers, and actually calibrate to properties that we know of our own sun these computational models. So on the right here, I have a diagram which on the x-axis, the bottom axis shows the effective temperature, and the y-axis shows the surface gravity. So these particular parameters are not super important other than to say that we've been able to measure them for our own sun to some degree, and then you can run computational models, which are these sort of blue patches within this parameter space, where you can run full-scale 3D models and then match them to what we know about our own sun to constrain and inform what our models of stellar convection is, and then apply that to many different areas. And so it's this idea of leveraging these computational methods connected to observation that have really shaped modern approaches to connecting to stars. Folks have also done things like estimating the age of stellar populations, where here I have another diagram. This one's called the color magnitude diagram, where on the y-axis, you can think of it as the brightness of a given star, and on the bottom axis, the color, you can think of it as a measure of where a star is in its evolutionary phase. And each little dot shown here is actually observational data, which folks have then overlaid a solid line, which comes from a theoretical stellar model. And so folks have been able to constrain the age, for instance, of this population, shown here by these dots, using models which rely on different numerical recipes and so on. So folks have been applying this to many different problems of connecting observation and constraining that using stellar models. But within those, there's a lot of uncertainties, and those really motivate a lot of the work that a lot of stellar astrophysicists are concerned with these days. How can we minimize these uncertainties, present new novel approaches that allow us to push forward our predictive capabilities and connecting data to observation in this way? So speaking more in detail about some of the challenges in modeling the life and death of a star, I want to bring this back to this image that I really like to show. It's an image of the atmosphere of Betelgeuse, which is a massive star you might be familiar with. But at the bottom part of this image, so this is a direct image from Hubble Space Telescope. In this image, there are relative scales at the bottom that sort of give a sense of the challenges that folks are faced when we're trying to build computational models of stars. And so the first scale shows the size of the star, of course, in the image, and below that is the size of Earth's orbit. So the orbit that we take around our own sun, and then for scale reference, Jupiter's orbit is shown there as well. So stars get really big in the late stages of their life, in particular shown here with the atmosphere of Betelgeuse. And so one of the challenges in modeling this is just simply the physical scales. And so things that are relevant to building these models is, say, the mean free path of light. How long does a photon or a light particle that's emitted during a reaction travel before it interacts with something else? That's on the order of a few centimeters if you make some approximations. Um, and then you have things where stellar envelopes, get to the scales of, like you showed here on the right, something hundreds of solar radii up to thousands, where we have something you're trying to revolve. You're trying to simulate something that spans an order of potentially 13 orders of magnitude. The timescales are also really challenging as well. So, for instance, in the sun, some of the timescales you might be concerned with is the nuclear timescale. So, how much time would it take to radiate all of the energy of the sun away? That's on the order of about 7 to 10 years. And then you're also concerned with the dynamical timescale. And these are usually relevant for convection. So, how well do you capture what's happening as convection moves and mixes material around? That's on the order of 10 to the minus 4. So again, something on the order of about 13 or 14 orders of magnitude in time now. And then computational limitations are a really big thing. Having access to these resources for studies is a challenge. And there's different explicit and implicit ways of solving these equations that govern the structures of stars. Some are limited by how fast the material is moving. Some are limited by variations in the structure. So there's different approaches you can take, but still, nevertheless, the end sort of goal, or the point that we want, is that you need a computational stellar model that can finish in less than the age of the universe. And if you try to capture all of these scales, whether it be time or length, in a complete model using modern computational tools and physics, it's just not possible, or at least not in a simulation that can run in less than, say, a few billion years. And so some of the modern approaches to modeling stars is taking these different evolutionary epochs in a star's life and separating them into unique components where you can focus on one particular phase, and you can build an overall model that leads to a general deeper understanding of the complete evolution of a star's life. And so throughout this talk, I'll be talking about 3 specific epochs that we'll focus on, that I'll highlight some of the work that's been done in those relevant areas that have helped build these models and advance our understanding in this way. So one of the first epochs is the lifetime. So here we're talking about the main sequence of a star, which is when a star is burning hydrogen into helium. So for a high mass or massive star, which is what I'll be focusing on for this talk, those are stars that are about 9 to 10 times the mass of our own sun. And so these are unique, and they evolve in a unique way. But for a massive star, that's about it'll spend its lifetime on the main sequence for about 90% of its life. And so trying to understand that bit is really unique in looking at that particular epoch in that star's life. You can also focus on the fate. So eventually, once that star evolves towards the end, if you will it explode? If so, how will the explosion look like? So a massive star will often end its life as a core collapse supernova explosion. And so I'll talk a bit in more detail about what that means in particular. But there's an entire subfield of which I'm a part, where you focus just on that end fate, and you try to connect that to either the previous or the later epochs of the star's life. And also of interest, and I'll talk about this a bit more, is the remnant phase. And so recall that a massive star will explode and potentially leave something behind. Um, there's a lot of work to be done on understanding what is the remnant that's left behind, and what is the subsequent evolution of that remnant. Because recall, I mentioned earlier that these remnants can then produce their own transient, where, say, you have um, 2 neutron stars that are formed, and then eventually coalesce and merge, and then create a new transient that creates unique elements that were not created in the initial supernova explosion. And so I'll go into more detail the rest of these, but that's sort of the idea that I'll have for the remainder of this talk, is walking us through these different epochs and highlighting some work in each of these different regions. So I'll start by talking about some work that's been done on stellar envelopes. We mentioned how large the envelope of a star can get relative to our own sun. So I'll highlight some work on that. I'll talk about advanced burning stages near iron core collapse, which is a big part of what my work's been concerned with recently. And then I'll go into talking about the fate, where we talk about modeling the actual explosions of the massive stars. And then I'll highlight some work in binary neutron star mergers that sort of showcases how remnants are being studied and informing different parts of a star's life. Starting off in this lifetime epic, if you will, there's a few sort of evolutionary epics that we might be concerned with in modeling massive stars. And here on the right, I have a schematic diagram, which is not to scale, of a massive star, the interior of a massive star, where it forms sort of this onion-like structure, which has been called in the literature, where you have, say, the most dense elements being formed in the center, and the previous burning stages overlie that core. You have silicon, oxygen, neon, up into different elements, lighter elements as you move out. But again, we're reminded of the different timescales for each of these burning epochs, with each subsequent burning phase being more energetic and taking less time to process that material. So past the main sequence, you'll have the massive star, become what's called a red supergiant. And this is when the core contracts, it continues to burn heavier and heavier elements, and it'll grow significantly large in radius, on the order of hundreds, potentially thousands of solar radii, which is what we saw when we were looking at that diffuse atmosphere of Betelgeuse in that image from earlier. Yeah, so our stars, onion skins. I don't think so, but I'll talk into more detail about this. But this is why this is sort of a simplified approach to visualizing what the interior of a star might look like, a massive star. So I want to start off by looking at some work that was done by a group at UCSB, led by Yanfei Jiang. It was a result in Nature in 2018, where they modeled in 3D the evolution of the massive star's envelope. So this very diffuse, very extended envelope that we mentioned, they did that in full 3D using state-of-the-art computational tools. And so some of the things I like to point out with this is, in the top left, they have the time in hours. So when we're thinking about time scales that are being evolved here, on the order of hours. The top right, we have solar radii. So the scale there is 2 scale. It's 50 solar radii for that particular length. And then we have a very large range in the gas density, which is being visualized here. But this is the exterior of a massive star, as realized by a simulation that allowed them to come to some conclusions that can be connected to observation. And so one of the things that they found was that the 3D variations at the surface, so these little ripples, if you will, that they found when performing their simulation, can actually lead to outbursts. And so they lead to changes in the luminosity of the star over time that's not seen in simplified models. And so now you're having a scenario where a 3D simulation is suggesting or showing something that's different from these simplified models, and potentially connects better to what we observe in observations when we look at a star and observe some curious behavior taking place. So again, for sense of scales, we have the gas density here with the color bar, the lowest value being on the order of 10 to the minus 12, the highest 10 to the minus 5. So this is very diffuse, very low density gas that they're having a model, which presents a very big computational challenge. So the next question you might ask is, what about the inside of a star? So the envelope is tricky. We know that. What's going on inside the star when it's in its red supergiant phase? So I want to call back to this image that we showed earlier of Betelgeuse, where, some time ago, this was sort of the state of the art that we had for massive stars when we were visualizing them directly, is this sort of pixelated blob from HST, which was a great image back when it first came out. It was actually the first direct picture of the surface of a star other than our own sun. So it was very groundbreaking in that way. But you have to wonder now, how can we go from an image like this, or at least how can we couple our models to an image like this, so that our predictions from our models can match with what we can infer from observation, and connect them to overall advance our understanding. And so talking a bit more about the final phases of a massive star's life, you have to think about the red supergiant phase. And so I mentioned this a little bit earlier, but once a star evolves later in its evolution, it's a massive star, it grows this iron core, this core that's primarily composed of iron, and then eventually that iron core continues to grow in mass until it reaches a critical mass. Um, and then pressure sources are actually removed from the star, and thus begins the end of the star's life, where you begin to start a phase called iron core collapse, where that core becomes dynamically unstable. It begins to fall inward rapidly on the order of a fraction of the speed of light. Then it collapses on the order of less than a second. And then it launches a shock, because of this collapsing core, creates a bounce, launches a shock, and that shock is eventually what drives that stellar explosion if it's successfully heated by that core that was created during the collapse. And so you might ask the question, can we predict when a star will explode? We have this image like Betelgeuse, but then you have something that's happening on the order of a second. How do we make our models useful to be able to predict when a star might explode? Well, what I'll say is that we can simulate the moments before collapse using state-of-the-art computational tools that have benefited from decades of work in preparing and these methods, these computational methods, and modeling stellar plasmas. And so one of the things that you can do is you can start from a more simplified initial condition, which is what I'm showing on the left, which the details of this graphic is not important other than to show that it's a line graph. So you can run a stellar evolution model, a 1D model that's vertically symmetric, a very simplified, but also complex model that incorporates tons of physics, but doesn't quite capture things that require which require full 3D models, so something that is not vertically symmetric. So you can start from something like on the left, you can map it into a multi-physics code, a very large scale simulation code, and you can realize something that looks like this, where you have the velocity field shown for an initial condition of a 15 solar mass star, so a massive star, 7 minutes prior to collapse. And so what we're looking at here is that burning that's taking place above that iron core that's making it grow in mass and then eventually reach that critical mass to where it collapses inward on itself. And so this is something that we were able to show, and just for scale here, we have the scale is actually to scale for the simulation. It's at a value of about 0.1 solar radii. And so just to give you an idea of this scale versus what we were looking at earlier when we were looking at 50 solar radii for the surface envelope, these are the different physical regimes that we have to pick and choose if we're trying to get a fully comprised model that is able to capture the different physics and these different relevant epochs. And this is the work I put out back in 2020. And one of the things that we're able to do that moved us beyond sort of that first model as we started to look into these models in detail is we wanted to characterize the convective motions. And so we started out again with this sort of initial condition that was spherically symmetric. It was 1D. We mapped that into our code, and then we were able to evolve that in time. This time we started 10 minutes before collapse. We were able to evolve that in time and start to get a detailed understanding of how non-onion-like these models are when they're undergoing this nuclear burning that's taking place in the advanced stages of a star's life. And so the same scale as the previous slide. So some of the things we observe are that we have large-scale motions. We have things happening in these simulations that really deviate from either this onion-like model or at least just what the 1D models might predict. The more simplified models might predict. You can capture mixing never seen before. So you actually, if you look at this lighter material, it's actually being mixed from the upper shell into the lower one. So you have material that is otherwise not predicted to be mixed in or entrained into these other regions. It's actually taking place, definitely not captured in a more simplified model. And we can start to think about, what are some of the signals before death that these models might suggest. So these will impact things like the pre-supernova neutrino emission. So as this core gets more dense, it starts to emit more particles that can be detected. But what it passes through as it moves outwards and then potentially towards a detector here on Earth, that will be impacted by what that structure looks like, that not so onion-like structure looks like. So see, these are some of the things we're starting to look into more detail in these works as we evolve these models and get a deeper understanding of the interior of a star in those moments before collapse. One of the next things that we were able to think about as we sort of built these models um, to become sort of a more definitive model, a complete understanding of what's going on, we wanted to look at the impact of rotation. So we actually know that most stars, most massive stars, especially, will rotate, whether it's slow or rapidly rotating. It will have an impact on the subsequent evolution. So we evolved another model starting from these initial conditions. We were able to model this rotation in this star and actually look at how that qualitatively affected the result, similar to or in comparison to the non-rotating models that we had previously. Some of the things that we found is that rotation can change the outcome. And when we talk about outcome here, we think about in detail, we think about how the angular momentum is sort of transported and where it moves as it is evolved in time. And so we're finding that these results are challenging simplified models, and that um, angular momentum is being moved and sort of pushed around by convection in 3D in a way that's not captured in 1D. And this is something that has very big implications for which type of remnant you might form, actually. And so this is something we were really excited to see out of these results, and it's sort of setting the groundwork for these more definitive models where you start to take in different pieces. You take in rotation. Stars are also magnetic. We're excited to start incorporating magnetic fields in our star in our stellar models. But this is really setting the groundwork as we build these next generation of models. Um, yeah, so that brings me to one of the first points that I want to bring up is that, or takeaways, if you will, of this lifetime section, is that stars are less onion-like than previously thought. The degree to which they're not onion-like is something we're working on, but that has a lot of implications for things like mixing, the final state of the star before collapse, and can impact our predictive capability that we want to try to leverage to tie in with observation. These next generational models, like some work I've shown from my previous studies, or that other people in my subfield have looked at, specifically the envelope simulations, can really get us to that next stage. So now you might ask, what about the explosion? So far, I've stopped them when they're about to explode each time. And so this brings me to the next section where I want to talk about some of the fates. And so here I have some of my favorite images of 3D core collapse explosion models, where if you look at close enough, you might see that collapsed core, that protoneutron star in the center. In the top middle image, it's actually peaking. It's the purple core in the center. These are visualized in different works, but there's a lot of challenges that go into modeling the explosion of a massive star. Part of it is magnetic fields, which I mentioned earlier. So magnetohydrodynamics, as it's called, and there's a whole field of that, and folks are thinking of very creative ways to address that problem. General relativity, so how you treat gravity, is very important. I mentioned that these things collapse at a fraction of the speed of light. Turns out that can actually influence some of the properties of the star as it continues to explode. So Boltzmann neutrino transport, that means how you actually track the transport, the material that's heating, the particles that are heating the explosion. And so you can make different approximations for that, but the approximations you make could potentially lead to a qualitatively different result. The microphysics, so things that could be measured inside the lab, potentially, or extrapolated to like nuclear cross sections and stuff. All of these pieces go into building a core collapse model and present current challenges that folks are making a lot of progress towards. So when we talk about a definitive model of core collapse supernovae and some of the challenges that we're facing, we want to think about what's motivating different directions and how we're calibrating. And so one of the things I like to think about as sort of open challenges that are making us think of unique ways to model these stars is shown here in this diagram on the right, where I have on the x-axis is the post-bounce time, which is sort of an indicator of the start of the explosion. The y-axis is the diagnostic explosion energy, which here is in units of beta, which is about 10 to the 51 ergs. That's not important. The main thing to point out is that when you take populations of observed supernovae and you measure, you make estimates of the explosion properties, including the energy, and then you compare that to all of these lines shown on the right, which are the results of 3D sort of state-of-the-art explosion models, the observations lie above most of these lines. And so you might argue that you might need to run these simulations out longer, but in mass, it's shown that these models, at least where they are now, are significantly below what we expect for the energy um, of core collapse supernovae. So this is an open question that we have in the field right now as we work to build better models that are in closer agreement. We can also have cases where the model fails to explode. So folks have written entire papers on stellar explosions where the shock actually recedes and then does not drive a successful explosion, a stellar model. This results in a failed supernovae, um, which we believe can happen. But when you have a sort of initial condition that you expect to explode and it doesn't, this sort of this presents some challenges with what you observe, the observed properties of the progenitors or the star that eventually exploded in nature in space. And so having these agree with each other, models we expect to explode that don't, and then having these energies match, these are all open challenges that are motivating a lot of questions that we're addressing in the field. There's also this idea of what happens to the remnant that's left behind. It's really hard to model these simulations from explosion all the way to remnant formation to potential merger. So again, I mentioned folks will sort of break up those different epochs, but these also present a very large area of uncertainty within the definitive model of core collapse supernovae. And so one of the things that I've been really excited about is moving on beyond simplified initial conditions. So in my work, I've really been pushing moving beyond some of the 1D initial conditions you see on the left, where you start like from a spherically symmetric model and you map that in, and then starting with something more like this. So recall our simulation from earlier that was taken from the first 7 minutes before collapse. Starting with this on the right instead to build a more complete model, a less onion-like model that could potentially get us to something that is in closer in agreement with observation. And so when you do that, you can build state-of-the-art models of stellar explosion. Where on the right, I have a visualization showing the explosion of a 15 solar mass star, where we're starting from these complex initial conditions that I showed from the previous slide to have sort of an end-to-end pre-collapse to post-bounce to explosion model that potentially gets us to a closer agreement. And we're actually finding that. We're finding when you explode these 3D complex initial conditions, you get more energetic models that are in closer agreement with observation. You get something that looks like the shock morphology or the expansion as these shells move out that looks a lot closer to what we observe in nature, these complex structures. And we're also observing large scale flow, which has implications for the remnant that is left behind and that is eventually formed. So this presents a potential solution to some of the ongoing challenges in the field of core collapse and exploding massive stars that can shed some light on what is a piece that we're potentially missing. And so that brings us to the next conclusion. Now, assuming stars are less onion-like, so the first conclusion, we can obtain more robust models of stellar explosion. So potentially it's that stars are not spherically symmetric. They're not onions before they collapse. If you assume that, you can build maybe more complete models and close this gap between our models and what the observations are showing us. So last question you might ask is, so what is left? So now I'll talk a bit about the remnants that are left behind potentially for these different massive stars after they explode. So I want to call back to this image that we showed earlier, where of the supernova remnant on the left, and then the neutron star the center on the right. So we're seeing these in nature, and we're observing these, and we're seeing these being left behind. What can we do to build our understanding of what the populations of these models are and how they might evolve in time? So one of the things that can happen is this, the fate of the remnant, if you will. The explosion of a massive star can leave behind a neutron star, which is this very dense collapsed core that was previously the iron core. It can leave that behind. It can also leave behind a black hole. So it turns out there's a maximum mass for neutron stars that eventually, if they exceed that mass, similar to the iron core, they form something else. And what they form is a black hole. And so if it crosses that mass threshold, some massive stars may produce black holes once after they explode or fail to explode. And what's often the case is that you can have stars be rotating and in binary systems, and so you can actually produce a binary neutron star system, like we're seeing here on the right, which is a visualization showing the merger of two neutron stars by work done by David Radici in 2017, where we're showing the density here for this binary neutron star merger. So the leftover sort of remnants of these massive stars that can actually produce tons of material in the process. One of the things I want to point out for this, which I think is really interesting, is we're talking about scales. So the color bar is mapped to density, which the highest value in this particular plot is 10 to the 15. Excuse me. So recall when we started, when we were talking about stellar envelopes, it was something like 10 to the minus 12. And so we really sort of have captured the entire range here in terms of density that folks have explored, all to paint a complete picture of the life of a massive star. And so neutron star mergers are very important, of course, because in 2017, there was this astrophysical transient 2017 GFO, which was the result of a binary neutron star merger, which was actually detected first in gravitational waves, GW 170817. And so LIGO and other such gravitational wave detectors, as they're beginning to come online and become more sensitive, they've really benefited from this combined use of computational models that allow them to match to observation and calibrate against each other, and, coupling with gravitational wave detection and optical emission that's detected by telescopes. And so this era of multi-messenger astronomy that allows us to use different tools to get a complete picture. So if you're a nuclear physicist, this plot might be interesting to you, but it has on the x-axis, it has the atomic mass for different isotopes, different elements produced in that merger situation, and the relative abundances. And you can actually match this to solar, which are these pink dots where the lines are from the simulation, which allows you to connect to observations and experiment, because you can measure we can measure different reactions in the lab. But if you're like me and this is not a particularly helpful plot, you might be more familiar with this one, where we look at the periodic table of elements, where here we have different elements being shown, of course, with each color in the box denoting a different transient or process that produces that element. And so you can see for orange boxes here, we have neutron stars, merging neutron stars, which are the orange boxes here. Those are sort of the bottom half of the periodic table. And we also have exploding massive stars, which I talked about earlier, the core collapse supernova explosions. Those shown in green, sort of the top half. But if you think about the life of a massive star exploding, creating two neutron stars, because there's two massive stars in binary, and then those eventually merge, you could say that massive stars are responsible for most of the entire periodic table of elements. And so this is where we like to sort of calibrate, think about where these different stars play a role in producing these different elements. And so one of the last conclusions I'll bring up is that stellar merger simulations provide a unique tool for connecting theory, observation, as well as nuclear experiment. There's a really exciting, as sort of next generation detectors and experiments, nuclear physics experiments come online. It's a really exciting future in that way. So to recapture sort of some of the modern approaches to modeling stars that we've talked about some of the lifetime epochs that folks can consider, whether it be the stellar envelope during a red supergiant, or the final moments right before collapse of the red supergiant phase. You can build models that help inform our understanding of stars overall. You can also look at their fates, and so we showed some core collapse supernova explosions, which allowed us to make predictions about what those might look like as we observe them. We also showed mergers of the remnants of binary neutron star systems that might be realized in nature that we're shown to also be able to connect to observation and experiments as well. So that brings me to my conclusions. I want to sort of retell what we kind of talked about, this story that we went through, that stars are less onion-like than previously thought. And these next generation models that are sort of starting to pop up that are capable now because of new techniques, modern approaches, new algorithms, whether it be looking at the stellar envelopes, the very diffuse material, or deep into the stellar interior, they can reveal these differences and allow us to start looking at those in more detail. And so if you assume that stars are less onion-like and you now build 3D explosion models from that, we show that these models can actually help drive explosions that are closer with agreement with observations. And so this new generation of relaxing this simplified approach to something that's more self-consistent and is more representative of a star near collapse. And then lastly, we talked a bit about how the late time stellar merger simulations can provide another unique connection between theory, observation, and experiment, in addition to some of the ways that explosion models and sort of the lifetime models can. But together, they're all sort of advancing our complete understanding of the different stages of a massive star's life. So my last slide, I wanted to bring it back to where we started with this composite image that we talked about, which hopefully, if you find yourself in a similar situation, seeing something like this, the Milky Way in the sky, that hopefully after this talk you have a deeper understanding of the role that stars play and galaxies like our own Milky Way and galaxies throughout the universe. So with that, I'll close and be happy to answer any questions. Thank you.
Thank you so much, Carl. This has been an awesome talk. So, thank you very much for, of course, the captivating simulations and imagery and adventure. Now, we do have a few questions coming your way. I'm not sure if we'll be able to take all of them, but I'm going to go ahead and pass you over to Betty for a question session from YouTube.
Hello, we have a number of questions actually. The first question is, for computational models, does quantum computing offer any future promise to create more detailed models?
Yeah, so that's a really good question. I think the answer is yes. I want to say I'm not a computational or a quantum person, but I think any way that we can speed up calculations is something that will allow us to push it further. Right now, sort of the state of the art that folks are really interested in is leveraging GPUs, processing units, and porting sort of old legacy codes that have traditionally run on CPUs to port their, say, hydrodynamics or gravity modules to be on GPUs, which can evolve and run these simulations much more efficiently.
Another question is, well, actually, there's a comment, and this comment is from Zapfan, and he's from the west coast of Sweden, and he writes, stars are like ogres, they have layers.
This is true, yeah. That's a reference I actually missed. I will update my talk right now. That's really good.
Okay. Another question is from Ennio Salucci. If iron builds over time, what happens that makes the collapse so quick?
Yeah, that's a great question. So iron is built. So these timescales sort of change as these isotopes burn at different rates, if you will. So the main sequence is about 90% of the star's life, but as you get towards the end of a star's life, you have something happening on the order of days. And so the collapsing being as quick as it is has to do with the density of the material and how fast it's able to move inwards. And it's quite complex because you eventually have this what's called a homologous inner region of the core and an outer region of the core. And so the core becomes complex. You have one moving at supersonic speed, one not. It's a very complex situation, but it all has to do with the density of the material that allows it to evolve in that way. So it happens very fast. Being able to capture it in a simulation is quite challenging.
The next question is from York University Observatory, and it's, what's the largest or most time-consuming simulation you have ever run?
That's a really good question. Yeah, so I've run a simulation that's used about, I want to say something like 60 or 70,000 CPUs at Argonne National Lab. And then that required a bunch of restarts, and it took about 6 to 9 months to run. Part of that is waiting in the queue, because the queue gets to be about 5 days. You run for 1 day and then you restart. So that's the process. But overall, it's taken some few months of continuous running time for these very large scale explosion simulations.
The next question is from Ennio Salucci. Can a failed supernova be detected?
That is a really good question, and is actually a very active field of research. So there's, during collapse, during bounce, there'll still be a bounce, and neutrinos will still be produced. And so I think the prospect there is that if there's one close enough and it's failed and neutrinos are produced, potentially that's one way to detect it. Optically, it would be a different story. It would have to be what happens. It would depend on what happens to the remnant. In most cases, it'll probably form a black hole. But there's a lot of people looking at what those transients might look like, observational signatures of that. And so one of the ways that they really need to be able to do that is leveraging a lot of models. So folks are running models of failed supernovae, but I think there are prospects, yeah.
Another question is from Chris Vaughn. How does the star's rotation affect its non-onion-like aspect? Would rotation add symmetry?
That's a good question. So it depends which epoch you're in. So for instance, for the models that I was showing before collapse, it turns out the rotation can be rapid, but in terms of the shell burning simulations or the layer burning simulations, rotation never quite gets rapid enough to significantly change things. What it does change is you might have something where it becomes more oblate, so it becomes kind of squeezed out at the equators. Where you do see potential symmetry imposed is after bounce. So once the explosion started, you get very rapidly rotating neutron stars, which can potentially create these jets where there might be some symmetry about the axis of rotation. That requires a very rapidly rotating star to collapse, but that could potentially play a role as well.
And I think this is the final question. It's from Lewis R. Can you incorporate the issues of dark energy, etc.?
That's a good question. So I think it's a little outside of what I work on. I know that folks have been doing studies where they've been looking at the properties of these protoneutron stars and how you might use them as, I guess, probes for types of very dense, strange material in the core of these neutron stars. Because we're simulating things that are very, very dense. And so if you observe a neutron star and it has some type of properties, whether it be how it's cooling or what its surface properties are, you can start to sort of challenge models like different strange type of material. But I haven't been able to incorporate much of that into my work. But I know folks are looking at things like that.
I think that is it for the questions. Thank you very much. Your answer and your talk was fantastic.
Thank you.
Thank you once again, Carl. I think it's you could definitely stay here for a while talking about collapses and supernovas and other disasters. I'll just go ahead and round off and say this is a big thank you from all of us tonight. And I'm going to go ahead and hand over to the president of Toronto Centre RASC, Tom Luton, to finish off the evening. Take it away, Tom.
Thank you very much, Elena. Well, good evening, everybody. Hope you're all doing well. We've got a few announcements, so we'll just get things rolling. So as Elena said earlier, we've got two types of meetings. We've just had one of our speaker nights, and in 2 weeks, we're going to have one of our recreational astronomy nights. As if you're watching us live, please say hello in the chat. Enter some questions for presenters, as other people have done. If you're a new member, please introduce yourself. And if you're coming to us from far, far away, let us know where you're visiting from. So, as I said, our next recreational astronomy night is on the 4th of May, Star Wars Day, at 7:30 p.m. Arnold Brody will be discussing the sky this month. Ron McNaughton will
Yeah.
be discussing stimulating durable astronomy clubs in high schools. And we've got one empty slot available. If you'd like to present something, please contact Paul Markov. Our next speaker's night is Wednesday, the 18th of May, 7:30 p.m. Dr. Lori Russo-Neptune will be giving us a talk. We don't have the full title of the presentation yet. We'll keep you posted on that. But it'll be here live on YouTube. Coming up at the David Dunlop Observatory in the coming days, on April the 23rd at 8:30 p.m. Is DDO Up in the Sky. There's a $12.76 registration fee. Links to that can be found at rascto.ca. DDO Astronomy, Sunday Stargazing on April 24th, 12:30 p.m. to 1 p.m. $6.78 fee. Again, registration online with the links set on our website. Now, effective the 1st of April, the Toronto Centre has restarted outdoor public outreach. We're recommending that volunteers and visitors wear masks to all of our events. We recommend that telescope operators disinfect their eyepieces, their focus knobs, and any other touch points like a step ladder with a 70% rubbing alcohol following each visitor or family unit. We are requiring visitors to disinfect their hands before touching any information booth literature. And when deciding whether or not to participate in outdoor events, all members should consider their personal health and comfort first. As for the rest of our operations, there are no changes at the moment. We are going to be online with our recreational astronomy nights and our speakers nights for some time to come. So, coming up on Friday, May the 6th at 6 p.m. to 11 p.m., we'll be having a public stargazing session at Millennium Square in Pickering. Join us and our sponsor, Durham Skies, for an evening of free public stargazing along the north shore of Lake Ontario. Observe the moon, stars, and a rare chance to see Mercury. Now, that's only before 8:30 p.m. Bring your own telescope. We'll be happy to help you set it up and aim it at the moon. Reminder that temperatures down by the lake can be a little chilly, so dress appropriately. Please check our website for a go or no-go decision based on the weather before heading out. So, our observing sessions at Bayview Village Park and Long Sault Conservation Area and Ontario Science Centre are suspended until further notice, not because of the pandemic. We're still trying to find someone who's willing to run our observational activities committee. This person will help run these sessions, make weather go or no go announcements, and will make a quick report to, is responsible for making a quick report to the Toronto Centre Council of what happened the day after. We've also got a few members of the committee who've assisted in the past who are more than able and willing to help get you started if you're interested. Please drop me a note at president@rastio.ca if you're interested in volunteering. The Carr Astronomical Observatory is open. Access to the facilities are for members and their families only in a non-communal fashion. The total site occupancy limited to 10 bookings and up to 25 individuals, with one person or family upstairs in the house, with the rest either as day use, not staying overnight, or camping in trailers or tents. The full details are on the website. Please read everything before you make your booking. So, we're also looking to fill a few other jobs in addition to our observational activities chair. We're looking for a chair of the Light Pollution Committee, the Volunteer Committee. We're also looking for a Marketing Committee chair and some committee members to help that person out. The AV committee, the wonderful folks who have put together this presentation for us this evening, are also looking for some assistance. The education and public outreach are also looking for some assistance as well. We may be doing some virtual star parties in the future, and we're always looking for telescope camera operators who can help out. Again, drop me a note if you're interested at president@rascto.ca. Quick shout out for the benefits of RASC membership. You can renew online at secure.rasc.ca. There is a RASC emergency fund if you're a longtime renewer, but there have been some issues that have cropped up as a result of COVID. Gift memberships are also available. Contact the national office at mempub@rasc.ca for full details. And with that, I'd like to wish you all a very pleasant evening. I'd like to thank you for joining us. You can please follow us on all the forms of social media that we've got listed here. If you like what you've seen here on YouTube, please like and subscribe. Click the notification bell for future updates. Be safe, keep looking up, and good night.